Okay, let's just dive right in. The sources you pulled together for this they're incredible.
They really are.
They stretch across millennia of human thought, from the earliest philosophy right up to modern quantum cosmology. This feels like a huge intellectual mission, really. We're asking the most foundational questions. What is matter? How does it move? What is the universe even made of?
It is. Our mission today is to trace how these bedrock ideas of existence were defined and then tested, and frankly, sometimes smashed and rebuilt.
And we're going to be moving all over the place, right? From indivisible particles to...
all the way to Einstein's radical idea of mass-energy equivalence, and even the fractal geometry of the cosmos.
It's basically the story of how we learned what reality is, one radical theory at a time. And to start that story, we have to go way back.
All the way back. 5th century BC, where this fundamental debate over matter and change really kicks off.
And that begins with the idea of the atom, the indivisible piece.
Yeah, atomism. It's arguably the first truly robust scientific hypothesis. It starts with Lysippus and his much more famous student, Democritus.
And their view was so remarkably physical, so mechanical. They proposed that all matter is made of these infinitely many tiny indivisible particles,
which they called atoms.
Right, atoms, and they're all just floating in a complete void.
It's an elegant concept. It explains all the diversity we see without needing some, divine force pulling the strings.
And Democritus gave these atoms actual physical properties. They weren't just theoretical dots.
Not at all. He said they varied wildly in form, in order, in posture. If you could zoom in, you'd see atoms that were convex, concave, some with tiny hooks, others like little eyes.
And this is the part that I find so surprising for a modern listener. He connected human perception, our senses, directly to the shape of these atoms.
He really did. For example, he theorized that the sensation of bitterness, that taste, it was caused by small, angular, jagged atoms physically hitting your tongue.
And
Sweetness came from atoms that were larger, smoother, and more rounded. It's this incredible attempt to connect the macro experience to the subatomic structure.
But this materialist mechanical view, it wasn't the only game in town.
Oh, not even close. It was a direct, really radical challenge to one of the most powerful philosophical schools of the time.
The Eleatic school.
Exactly. They offered the complete opposite worldview.
So tell us more about them.
Well, we can trace it back to Parmenides, who many historians consider the first pure rationalist. His core principle was absolute and profoundly simple.
Which was?
What is and what is not.
Okay, so what are the implications of a statement like that?
Well, if nothingness, the void, can't exist, then everything has to be one continuous eternal substance.
Which means change is an illusion.
Exactly. The dynamic changing world we see with our senses must actually be this one, or being, eternal, whole, immovable, and invisible.
So for Parmenides, knowledge has to come from reason, from pure logic.
It's the only way, because perception, our senses, they're inherently flawed and contradictory.
That is just a staggering philosophical split. It's basically asking if you trust your eyes or your mind.
It is. And it's wild to think that this whole debate, atoms versus the unchanging one, really forms a foundation for so much of Western thought on reality.
And these ancient ideas, they didn't just stay in old scrolls.
No, centuries later, they found new practical applications. Epicurus, for instance, he brought back Democritus's atomistic theories.
But not just for physics, right?
Right. He used it to help people take responsibility for themselves and for their own happiness. If the universe is just atoms in a void, there are no meddling gods, no fate.
Just physical cause and effect.
Which is an enormously liberating idea for a person.
That's a fascinating connection. Okay, let's fast forward a couple of millennia. We're moving into the classical scientific era, where we stop just debating existence and start, quantifying it.
And this brings us to the classical revolution in defining mass and movement.
Before the 17th century, the idea of mass was just confused.
It was a mess. It was generally just called weight, which bundled together two totally distinct things.
The actual amount of stuff.
Right. The physical quantity of matter and the downward force it exerts in a gravitational field.
And Galileo was the key figure in untangling this.
Absolutely. Everyone knows the story of him dropping things from the tower, but his real insight was focusing on free fall.
He showed that the time it takes for something to fall is independent of its mass.
Exactly. If you ignore air resistance, a feather and a cannonball fall at the same rate. And that simple observation, it finally resolved this ancient paradox about heavy and light bodies.
So it showed that the property of matter that resists acceleration and inertia is perfectly balanced by the property that attracts other bodies' gravity.
Then came Isaac Newton, who formalized it all. He defined two distinct concepts of mass,
Inertial mass
which is what determines how much an object resists a push, F equals ma,
and gravitational mass.
which determines the attractive force between bodies. The key takeaway, the thing that would underpin all of future physics, is that experiment after experiment showed these two masses are identical.
And that identity is called the equivalence principle. Why is that so essential?
Because it paved the way for general relativity. If inertial mass and gravitational mass are exactly the same, it suggests gravity isn't just some force.
It's a fundamental property of space and time.
Right. Einstein later took this equivalence as a given and defined gravity not as a force acting across space, but as the geometry of space-time itself being warped by mass and energy.
But even so, for centuries, people resisted that idea. Newton's gravity was still challenged by those trying to find a purely mechanical, clockwork explanation.
Oh yeah, like the theory proposed by Nicolas Faddeau and Georges Louis Lesage.
So this model was an attempt to explain gravity as a push, not a pull.
Exactly, a deeply elegant attempt. The idea was that gravity is caused by these tiny, high-speed particles streaming through the universe from all directions.
Okay, so how does that create an attractive force?
Well, as these particles stream, they hit a large body. Since the body isn't perfectly transparent, the particles that bounce off lose a little bit of momentum.
If you have two bodies near each other,
They partially shield each other from the particles coming from the other side. That creates an imbalance. The pressure from the unshielded side pushes the two bodies together.
that sounds plausible. If you didn't know anything else, it seems like a very elegant mechanical solution.
It does.
So why didn't it stick?
It has a fatal flaw. For the model to work, matter can't be perfectly transparent.
Which leads to an effect called gravitational shielding.
Exactly. And this shielding would mean that the gravitational pull of a big object wouldn't be perfectly proportional to its mass. A denser Earth, for instance, should shield its own core, making its pull weaker than expected.
And what did the experiments show?
Highly precise experiments, like the Euclid's experiment, showed absolutely no evidence of gravitational shielding. Zero.
And that completely refuted the Faddeau-Lesage model.
It did. And it's a great historical anecdote that even Newton was conflicted about it. We know he privately called it the unique hypothesis by which gravity can be explained mechanically.
But he and Edmund Halley also supposedly laughed at it.
Yeah, because it seems so crude compared to the mathematical elegance of his own laws. It just captures that tension between a simple mechanical model and the more sophisticated math you need to describe nature.
And that very mathematical language was emerging at the same time.
It had to.
As the mechanics of the universe got too complex for classical geometry, a whole new system was needed. And that, of course, brings us to calculus.
We credit both Newton and Gottfried Wilhelm Leibniz for inventing it independently. But it was really Leibniz who gave us the framework that unlocked modern dynamics.
He had that breakthrough with integral calculus on November 11, 1675.
Yeah.
And we still use his notations.
We do. That elongated S for summa, or sum, and the D for differentia. That mathematical formalism really set the stage for the next great revolution.
The 20th century paradigm shift, where we go beyond planets and apples and dive into the tiny constituents of matter itself.
And that dive, of course, begins with the electron, the first fundamental particle we really identified.
It started with observations by Julius Plucker in 1859, right? He saw this strange radiation from a cathode.
It caused a phosphorescent light, and it could be deflected by magnets.
Proof that there was something flowing out of matter that carried a charge and was way, way smaller than an atom.
And those observations just ushered in the quantum era. By 1924, Wolfgang Pauli had explained the structure of the atom using 4 parameters, but the last one was a mystery.
The Pauli exclusion principle.
Right, it worked, but nobody knew what the physical mechanism was.
Until 1925, with George Uhlenbeck and Samuel Bootzman.
They provided it spin, the intrinsic angular momentum of the electron.
Which is a quantum property, meaning it's not really like a tiny spinning top.
Not really, no. But it dictates how electrons behave inside the atom. And what's truly fascinating is what we know about the electron today. Experiments suggest it's structureless and point-like.
With an upper limit radius of 10 to the power of negative 22 meters.
It's just It's hard to imagine anything smaller or more fundamental.
Meanwhile, on the macro scale, Albert Einstein was just completely reshaping the cosmos.
Special relativity in 1905 gave us time dilation, length contraction, and got rid of the idea of the luminiferous ether.
And led to the most famous equation of all time, E equals mc squared.
And the mass-energy equivalence, it's often taught just as a simple conversion, but its significance is so much more profound than that.
It's a statement of identity.
Exactly.
Let's unpack that. Why is it more than just a conversion formula?
Because it forces us to redefine what mass is. The mass of an object is generally not the sum of the masses of its parts.
Okay.
Instead, the rest mass is the total energy, kinetic, potential, binding energy, all of it, of all the components in that object's rest frame.
So like the classic example of an atomic nucleus.
Precisely. If you add up the mass of 2 protons and 2 neutrons, and then compare that to the mass of a single helium nucleus,
The helium nucleus is lighter.
measurably less massive. That missing mass is the binding energy holding the nucleus together. It confirms that all energy contributes to mass, and therefore contributes to the gravitational field.
That's a staggering confirmation of unity. And the verification of this new cosmic geometry came pretty quickly.
It did. Arthur Eddington provided one of the most famous confirmations by observing starlight bending around the sun during the 1919 solar eclipse.
It matched Einstein's prediction perfectly.
It did. And then, almost 100 years later, in 2015, we finally detected Einstein's predicted gravitational waves, those ripples in the fabric of space-time.
So back in the subatomic world, Paul Dirac's work in 1928 continued the revolution.
He was trying to reconcile special relativity with quantum mechanics, and his equation was just brilliant.
It provided a relativistic description of the electron.
Yes, and like all powerful theories, it generated a prediction that went beyond what it was designed to describe.
It predicted the positron.
Correct. The math naturally required a particle with the same mass as the electron, but the opposite charge.
The electron's antiparticle, which was then observed in 1932.
And Dirac's work also explained that quantum spin wasn't just some arbitrary number, it was an inherent relativistic phenomenon.
And it's moments like that, when math predicts reality before we see it, that physicists get pushed into the deep end of philosophy.
That is exactly what happened. Arthur Eddington, seeing the implications of the Heisenberg uncertainty principle, connected it to a defense of the idea of human freedom,
He started arguing for a kind of philosophical idealism.
suggesting that reality is basically mental, because you need consciousness to collapse the wave function and define what's real.
And Hermann Weyl, another giant of quantum mechanics, he also shifted his view.
He did. He started to see mathematics, his lifelong tool for defining objective reality, as merely a symbolic construction. He questioned if math could ever give us a final objective answer.
That's powerful. 2 millennia after Parmenides argued that reason alone reveals truth, 20th century scientists found that reason, in the form of quantum mechanics, reveals inherent uncertainty.
It's a beautiful link between the past and the present. Okay, let's shift gears. We've looked at the very small, now let's look at the incredibly vast.
Structure and scale. And this brings us back to an old riddle, Olber's paradox.
Why is the night sky dark?
Right. If the universe was infinite and static, every line of sight should end on a star, so the night sky should be brilliantly white.
Carl Charlier, in 1908, used the idea of self-similar nested structures to provide a mathematical answer. He proposed a cosmic hierarchy.
So stars form galaxies, galaxies form clusters.
And those clusters form superclusters and so on ad infinitum. And for this to solve the paradox, the average density of matter had to decrease as you went to higher order systems.
So the clusters are far enough apart that the total light stays finite.
Precisely. This idea of self-similar, iterated structures was later formalized by Benoit Mandelbrot into the field of fractals.
Which look the same no matter how much you zoom in or out.
And it's just incredible that Leibniz, way back in the 17th century, sort of anticipated this with his principle of continuity, natura non facit saltus.
Nature makes no jumps.
Yeah, he even used this analogy of infinitely inscribing circles within circles to illustrate the idea.
It really seems like no matter the scale, there's this underlying drive to explain how simple rules generate incredible complexity.
This brings us to a theoretical model called the action-reaction theory, or ART, which tries to formalize this.
Okay, so this theory says that nothing is really a new creation, but is constantly being built up from existing interactions.
It's an attempt to unify evolution and physics. The core chain of evolution it proposes is, well, it's highly conceptual.
So break it down.
But we think of it as a four-step cycle. First, opposition creates movement. You need friction for anything to happen.
Okay.
Second, movement creates chance. As things move, they encounter new states. Third, chance creates repetition.
If some encounters are favored, they start repeating.
Exactly. And finally, repetition guarantees ongoing evolution because those repeatable patterns become the building blocks for bigger, more stable things.
So it's a feedback loop. Friction, motion, patterns, and then new levels of complexity.
Precisely. And crucially, the theory says for this to work, there has to be some kind of basic intelligence built into the system. It needs a memory.
And how would that memory function physically?
The theory suggests it could be encoded in, say, sequential ring forms or maybe electromagnetic structures, allowing simple matter to remember what worked and adapt.
It's a model trying to bridge that gap between inanimate physics and the emergence of life.
And as we trace this vast intellectual journey, we have to acknowledge the immense human achievement involved. The work is truly global.
And nobody embodies that more than Abdus Salam.
That's right, a monumental figure. He won the Nobel Prize in Physics in 1979 for his work unifying the electromagnetic and weak nuclear forces.
But his impact went way beyond that one prize.
Oh, absolutely. His list of accolades, the Copley Medal, the Royal Medal, and the Nishani Imtiaz, one of Pakistan's highest honors. It just reinforces how universally recognized these contributions are. He transcended borders through the sheer power of his intellect.
What an incredible story. This relentless inquiry spanning millennia, from Democritus defining the indivisible particle,
And Parmenides arguing for the unchanging universe.
right through Newton's precise definitions of mass, the elegant flaw in the Fadio model, and into the quantum complexities of the 20th century.
Every single one of these figures, whether a philosopher or a physicist, was trying to define the relationship between the mind, the world we see, and that, mysterious X factor that governs reality.
And that connection brings us right back to where we started in the 5th century BC. So as you reflect on this deep dive, consider this provocative thought. Parmenides claimed matter cannot be infinitely divisible, that the fundamental thing must be whole. Modern physics currently treats the electron as experimentally structureless and point-like.
With a radius so small it's functionally zero.
So does this profound experimental finding, almost 2,500 years after Parmenides, suggest that maybe the deepest level of reality echoes that ancient idea? That the most fundamental entities are truly whole and indivisible?
Something to mull over the next time you think about what you're made of.